Okay, section 6.4 is on graphing sine and cosine. So our next three sections of this chapter are on graphing, and the way they're broken up is 6.4 covers graphing sine and cosine. 6.45 will be graphing cosecant, secant, tangent, and cotangent, and then 6.6 is on something called phase shifts. So it kind of gets broken down into three separate sections here. So the first thing we'll do, and we should be able to get through this in the next 20 minutes here, is let's graph y is equal to sine of x. Okay, so what we're doing is we're moving away from these angles in standard position here, and we're putting them on the x and the y axis. Okay, so on the x axis, this is our goal. The x axis are going to be the inputs. These are going to be angles, right? So we'll have 0, 30, 60, 90, 120. These are all going to be angles. And then on the y-axis here, we're going to have the value of sine at that angle. So y is going to be sine of x. Okay, so what we're going to do is take all of those angles in the standard position here, evaluate sine, and essentially we're going to roll this out onto the x and the y-axis. Now, anytime you don't know what a graph looks like, you can always start by making a chart of values. So we're only going to do this chart of values one time. This is the really long, painful way of doing it, but I want you to be convinced of the shape of the graph, and I don't want to just give it to you and say, here's a shape, you have to believe me, memorize this. I want you to see where it comes from. So we'll only do this the long way one time. Once we have the graph down and we know the general shape and properties, we can take the shortcut all the rest of the times. So what I'm going to do is I'm going to make a chart of values. So I'm going to have x, that's going to be my angles, and then y is going to be sine of x. So I'm going to strategically pick angles that we know how to do by hand here. What is the period of sine? What's the period of sine? 2 pi. Okay, so all I need to do is pick angles from 0 to 2 pi. And usually we like to do this in radians and not degrees. So I'm going to pick from 0 to 2 pi. And then we know sine is periodic, which means the shape of the graph is going to repeat. So I'm going to pick 0, pi over 6, pi over 2, 5 pi over 6, pi, 7 pi over 6, 3 pi over 2, 11 pi over 6, and 2 pi. I'm strategically picking these because I know what the graph looks like, and I'm picking the values that work out easily by hand. Okay, so again, once we have the general shape of the graph, you don't have to do this ever again, this chart of values, but I want you to be convinced. Okay, so the easiest ones to evaluate are our quadrantal angles, It turns out that our quadrantal angles, quad means 4. If we take the period, which is 2 pi, and divide by 4, those tell us where our quadrantal angles are. So these are the easiest ones to do. 0, pi over 2, pi, 3 pi over 2, and 2 pi. So let's evaluate these first, and then we'll do the other ones. So to evaluate the quadrantal angles, remember we look at a point that is a distance of 1 away from the origin. This is our shortcut. This has an x coordinate of 1, y is 0. Here x is 0, y is 1. Here x is -1, y is 0. Here x is 0, y is -1. Remember, in alphabetical order, these tell us cosine, sine, cosine, sine, cosine, sine, cosine, sine. So let's fill in some of these values now. So first up, we want to find sine of 0. Help me fill these in. Sine of 0 is equal to what? 0. How about pi over 2? What's sine of pi over 2? 1. How about pi? What's sine of pi? 0. How about 3 pi over 2? What's sine of 3 pi over 2? -1. And back to 2 pi, sine is 0. I'm going to refer to these points as my key points. So you'll see once we get the shape on the rest of the problems, I'll tell you your shortcut is let's plot the key points. The key points are derived from these quadrantal angles. To get our quadrantal angles, we'll always take our period and divide by 4. Now look at the pattern here, 0, 1, 0, -1, 0. This pattern is going to be really important. Because sine is periodic, we're going to just vary between 0, 1, 0, -1, 0, and then we'll continue 1, 0, -1, 0, 1, 0, -1, 0, over and over and over again. And our graph is going to kind of have this wavy up and down shape. Essentially what we're doing, because sine corresponds to this y coordinate here, we're taking this circle and we're going to unwind this circle on the x and y axis, and we'll end up something looks like that. Okay, these other points in here are not our key points. I just put some extra values in here to convince you of what the shape of this graph looks like, but I'll do these really quickly for you. Pi over 6 is 30. So to find sine of 30, we draw a triangle. We know our sides are 1, √3, and 2. Sine is opposite over hypotenuse, so that's 1/2. So I strategically picked the ones that worked out nicely that didn't have a square root in it. 5 pi over 6, we have the same triangle in the second quadrant. So we also get positive 1/2 because sine is positive in the second quadrant. I picked all the same ones. So in 7 pi over 6, that would be in the third quadrant, same triangle. But in the third quadrant, sine is negative, so we're going to get -1/2. In the fourth quadrant, 11 pi over 6, same triangle, cosine is negative. Okay, so those extra values in there are just to convince you of the shape of the graph. What's going to be important if I were to ask you to graph this by hand is that you put in these key points. Now you guys, lucky all of your homework is on my math lab, which means you have a graphing tool. But I would encourage you, as you're going through these examples on your homework, I would encourage you to practice graphing them by hand. If you're moving on to calculus or physics, this is going to be really important that you know how to do these by hand. All right, so any questions so far? Okay, so now what we want to do is take these x and y values and put them on the x and y axes. Again, essentially, we're taking these y values here and we're unwinding them, and we'll see what shape we get. This is our graph of y is equal to sine of x. Okay, the two things that are going to be really important to us as we're doing these graphs, and we'll talk about this a lot more over the next 3 sections, is we always want to label our x and our y axis appropriately. So what value should I put on my x axis and what value should I put on my y axis? These key points, the ones that are highlighted, came from our period divided by 4. Our period divided by 4 is because those quadrantal angles are what's most important. So what we're going to do is label our x-axis always by our period divided by 4. So I'm going to put 1 pi over 2. 2 pi over 2 is pi. 3 pi over 2. So I'm counting by pi's over 2's. 1 pi over 2, 2 pi over 2, 3 pi over 2. 4 pi over 2 is 2 pi. 5 pi over 2. 6 pi over 2 is 3 pi. And I ran out of space. In the negative direction, negative pi over 2, negative pi, negative 3 pi over 2. I'm copying the values from over here. Okay, so all I'm doing is counting by pi's over 2's and reducing as I go. The way we label our x-axis, I'll drill this into you for the next 3 sections, we always take our period and divide by 4. Okay, on our y-axis, let's figure out what needs to go on our y-axis. Looking at this chart of values, What's the maximum y value we hit? What's the maximum y value here? 1. What's the minimum y value we hit? -1. So it turns out here that on our y-axis, we'll put a 1 and a -1. Now, the reason why we never hit something greater than 1 and something less than -1 has to do with these opposite over hypotenuse, right? Sine is opposite over hypotenuse. The sides of those triangles can never have a ratio greater than 1. The hypotenuse is always going to be the longest side. All right, so let's plot in our points now. So I'm copying from here. Our first point was 0, 0. Our next point was 1/2, 1. Then we had pi, 0. Then we had 3 pi over 2, -1. Then we had 2 pi, 0. These are our key points. Our pattern for sine goes 0, max, 0, min, 0. This is one cycle or one period of sine. Now I'm filling this in with a smooth curve. The other points we had in our chart were pi over 6, 1/2, 5 pi over 6, 1/2, 7 pi over 6, -1/2. Those were to convince you that this shape looked like this. The other way we can see that this has a rounded shape is literally what we're doing is we're taking this circle, we're taking these y values here, and we're unwinding this circle. So this looks like a circle unwound. Sine is periodic, so that means this period, this shape, this pattern continues in both directions. So we have 0, max, 0, min, 0, and we would continue this wave shape in both directions. Okay, some other things to note. I put an arrow on the ends of my graph. This indicates this pattern continues towards infinity. So we would have this wave shape in both directions an infinite number of times. The other cool thing that one of my students taught me last year that I was like, pooh, mind blown after 12 years of teaching trigonometry, is if we turn this graph sideways and look around the origin, what letter does that look like? An S, S for sine. And what we'll see once we do cosine, cosine is going to be a C for cosine. Okay, so that looks like an S, S for sine, and we'll see that cosine has a C shape around the origin, C for cosine. Okay, so last thing we'll do here is list out the properties of this graph. And these are a lot of the terms you learned in Math 126. So the first property is the domain. Remember, the domain refers to the x values we're allowed to plug into a function, okay, on what values our function is defined. So if we look along this x-axis, this graph continues in both directions, which means our domain is all real numbers. This is our mathematical symbol for all real numbers. It's a capital R with an extra line through it. The other way of writing all real numbers is from -infinity to +infinity. Or you could literally write out all real numbers. Okay, so sine is defined on all real numbers. We can plug anything we want into sine. The next property is the range. Remember from Math 126, the range is the set of y values that our function actually hits. The range is a set of y values that our function actually hits. So looking along the y-axis, what's the smallest y value our function hits? -1. What's the largest y value our function hits? 1, and it hits everything in between. So our range is from -1 to 1. Remember, the brackets means we include the endpoints. Now, this is really, really, really useful. This says that for any angle whatsoever, if we plug sine, or if we plug any angle into sine, our output should always be between -1 and 1. Okay, so sine of any angle at all is always going to be some value between -1 and 1. This is a really good self-check when you're doing a homework or a quiz or a test. If you're asked to find sine of anything, whether it's sine of 45, sine of 270, sine of negative 500, your answer is always going to be between negative 1 and 1. Always. Really good self-check. Our next property is that this graph does have some symmetry. So again, we got to go back to 126. Let's just look around the middle. This helps a little bit. This graph is symmetric with respect to what? So what acts as a mirror? If it was the x-axis, this part would have to be reflected down here. If it was the y-axis, this part would have to be reflected over here. The origin, okay, so this is symmetric with respect to the origin. So if we look at the middle here, this part of the graph gets rotated around and looks just like this part of the graph. So this graph is symmetric with respect to the origin. Sine is what? Even or odd? Odd. Every odd function, the graph will always be symmetric with respect to the origin. So if you want to think about some easy examples from 126 to help you remember this, if we look at f of x is equal to x cubed, that's an odd power function. That looks like this. The odd number, this is symmetric with respect to the origin. It is true that if a function is odd, it always has some symmetry with respect to the origin. It works both directions. If it has symmetry with respect to the origin, then it's odd. The odd property, we saw that f of negative x is equal to negative f of x. All right, that's our definition of odd. Let's just take a look at our picture and see what that means. So if we, for example, look at pi over 2 and negative pi over 2, they have opposite signed outputs. So one is positive 1, one's negative 1. If we input opposite signs, so 3 pi over 2 and negative 3 pi over 2, they have opposite signed outputs. Our next property is that, as we've already mentioned, the period is 2 pi. So if we look at this picture, we should have one full cycle by 2 pi. Our next full cycle would be by 4 pi. Our next full cycle would be by 6 pi. So this pattern repeats itself every 2 pi on the graph. Our last property here is the intercept. Your book lists this out in a strange way. I would never ask you to list out the intercepts on a quiz or a test. The x-intercepts here, we can see our 0, pi, 2 pi, 3 pi. So your book just kind of does this dot, dot, dot. But we can see our x-intercepts are every multiple of pi. And then your y-intercept is 0. Okay, so last lecture, we graphed y is equal to sine of x. Today, what we're going to do is graph y is equal to cosine of x. And again, we'll do this the long way for one time through. And then once we've done it the long way and we see what the pattern is, we can use the pattern to graph things quicker. We don't need to do it the long way every time. Okay, so we know that the period of cosine is 2 pi. So what I'm going to do is graph from 0 to 2 pi, and then we'll repeat the pattern. So again, what I'll do is, this is a long way, one time only. We'll make a chart of values. And what I'm going to do is pick values from 0 to 2 pi, and then we know that that pattern repeats. So I'm picking strategic values for these angles here. I'm going to pick 0, pi over 3, pi over 2, 2 pi over 3, pi, 4 pi over 3, 3 pi over 2, 5 pi over 3, and 2 pi. Okay, so I'm picking the values that have outputs, these y values that work out nicely. I picked the ones without square roots in them just for the sake of demonstrating what this graph looks like. Okay, so the first thing we'll do is work on our quadrantal angles. Quadrantal angles. So the quadrantal angles, these key points, are always going to come from taking our period, which is 2 pi, and dividing by 4. So our period divided by 4 always tells us where these key points are. So that's going to be at 0, pi over 2, pi, 3 pi over 2, and 2 pi. I'm going to refer to these as key points, and you'll hear me say, let's put our key points on the graph. Once our key points are up, we can connect our graph with a rounded shape. Okay, so just a quick refresher. As you saw in the exam 1 study guide there, you did have some questions of evaluating these quadrantal points. So let's just remember how we used this shortcut. And again, this comes from these shrinking triangles. So what we want to do, our shortcut for these quadrantal angles, is we look at a point that's a distance of 1 away from the origin. So a distance of 1 away here, the x-coordinate is 1, the y-coordinate is 0. Here our x-coordinate is 0, y is 1. Here x is -1, y is 0. And here x is 0, y is -1. Okay, so our shortcut here, this allows us to have cosine sine, cosine sine, cosine sine, cosine sine. They go in alphabetical order. So when x is 0, cosine is 1. When our angle is pi over 2, right, that's 90, cosine is 0. When our angle is pi, so that's 180, cosine is -1. And when our angle is 3 pi over 2, cosine is 0. And then at 2 pi, we're back at 1. So you can see that our pattern looks very similar to our pattern of our key points from sine, right? We vary between 0, 1, and -1. Sine, we just do it in a different order, right? Sine, we started at 0, 0, and then moved up to 1, and then down to 0. So the reason why these key points keep coming up is because all of these are derived from the ratio of sides of a triangle. So as we saw last lecture, as we have those shrinking triangles, right? Here's where the adjacent side shrinks to 0. And here's where the adjacent and the hypotenuse approach the same size. The other thing you want to think about too is, right, all we're looking at for cosine is these x coordinates when our radius is 1. So what we're literally going to do is take this circle here, these x coordinates, and we're going to unravel it on the x-axis to graph this. These other points I put on here, you don't need to put all of these on your graphs. These key points are the important parts, but I put these in just to convince you of the shape of the graph. So let's evaluate these really quickly. All right, so help me out with this one. Pi over 3 is equal to how many degrees? Pi over 3 is how many degrees? 60, okay. So here's 60 degrees. We drop a perpendicular, forming a triangle. We recognize this as our 30, 60, 90. All right, let's point to the sides of the triangle. Here's some good review for the exam. You guys tell me the lengths of the sides. The side that's across from the 30 has length what? 1. Across from the 60 has length what? Square root 3, and what's the hypotenuse? 2, great. Now we're evaluating cosine of 60, so I did this on purpose. Cosine is adjacent over hypotenuse. I picked the angles that worked out nicely without a square root, just for the sake of drawing our graphs. Now 2 pi over 3, that's in the second quadrant, and I picked these angles on purpose. This has the exact same reference triangle with 60 here being our angle of reference, which means our answer should also be 1/2. And in the second quadrant, cosine is what? Positive or negative? What's cosine in the second quadrant? Positive or negative? Negative. All right. 4 pi over 3 is going to be in the third quadrant, same triangle, so we know we should get 1/2. And then our question is, in the third quadrant, cosine should be what? Positive or negative? Negative, good. And in the fourth quadrant, we'll have the same triangle, and cosine in the fourth quadrant is what? Positive or negative? Positive, good. Okay, and this should make sense as we graph, right? These are all negative grouped together. Our graph is going to be smooth and continuous. It shouldn't jump around a lot, so that all looks good. So again, what I'm going to suggest and what we're going to do on the rest of the examples in this section, we'll just graph these key points. These are just to convince you of the shape for this first time around. Any questions so far? Any questions so far? Anybody need more time on this page? Okay, so let's put all of these values onto a graph now. So we start by drawing our XY axes. And let me remind you guys that on your homework, you have a graphing tool. So this is going to be done electronically. But for those of you that are moving on to physics or engineering or calculus, I really, really encourage you to try drawing these by hand before you jump to the graphing tool. Okay, so try to do these by hand. You're going to need to know how to do these in your other class. So give these a try. The first thing we need to figure out is how to label the x-axis. To label our x-axis, we're always, always, always going to take our period and divide by 4. Always take our period and divide by 4. Now, the reason why 4 is because those key points came from our quadrantal angles, and quad means 4. Okay, so period divided by 4. So our period is 2 pi. Divide by 4, that gives us pi over 2. So I'm going to label by 1 pi over 2. 2 pi over 2 is pi. 3 pi over 2. 4 pi over 2 is 2 pi. 5 pi over 2. 6 pi over 2 is 3 pi. And that's plenty. And in the negative direction, I'll just copy that pattern. The next thing we should do is figure out how we want to label our y-axis. So if we look at our chart of values that we came up with on the last page, help me out with this one. What is the highest? What's the biggest y value our graph hits? 1. What's the smallest y value our graph hits? -1. Okay, so again, these 1 and this -1, this comes from the fact that we're looking at ratio of sides of a triangle. Okay, so let's plot on our points. First we had 0, 1. Then we had pi over 2, 0. Then we had pi -1. 3 pi over 2, 0. 2 pi 1. This is one full cycle, one period of cosine. We're going to connect this with a rounded continuous graph. It is rounded because, as I mentioned earlier, we're picturing taking that circle of values and unwinding it. Also, those other values for pi over 3, 1/2, 2 pi over 3, -1/2, hopefully those convince you of this shape. Okay, now we know cosine is periodic, so what we want to do is continue this pattern in both directions. And this is what our graph of, I should label this, y equals cosine of x. This is what our graph of cosine of x looks like. Okay, so this is periodic with period 2 pi, right? Our graph repeats in both directions. Now, remember, last lecture I put up sine, and one of my students last year showed me the coolest trick. If we look at this graph around the origin, and we turn it this way, right around the origin, it makes a C for cosine. Now remember, yesterday we did the same thing with our graph of sine, and when we turned the graph of sine sideways, we got an S for sine. So if you ever have a hard time remembering the difference between cosine and sine, you're welcome to use that handy little trick there. It's amazing, sometimes my students just have these really neat tricks that they've learned from their previous math teachers. And that's one that just like really stuck in my head. Oh, it's so cool, so cool. How did I go so many years without knowing that one? Any questions on how I got this graph of cosine? Okay, so let's list out the properties. The first property is that the domain, what we're allowed to plug into the function, the x values on which our function is defined, right? These are terms from Math 126. The domain is all real numbers. So if we go along the x-axis, we can plug in any angle we want into cosine, and it is defined. So this is our mathematical symbol for our real numbers. It's a capital R with an extra line through it, or you can write from negative infinity to positive infinity, or you could just write all real numbers. I won't ask you for the domain on your test, so don't worry about which of those are appropriate. But as you move on with math classes, any of these should be acceptable. The range is a set of y values that our function actually hits. The range is a set of y values that our function actually hits. So help me out with this one. If we look at our graph, what's the smallest y value our function hits? -1. What's the largest y value our function hits? +1, and hits everything in between. So our range is from -1 to +1. We talked about this last lecture about sine. This is really useful. What this means is that no matter what angle you plug into cosine, your output is always going to be something between -1 and 1. This is a really good self-check on a quiz or a test. If you're ever asked to compute cosine of any angle at all, you better get an answer between -1 and 1. If you get something that's like 1.5, you've done something wrong. Okay, so you should always get an answer between -1 and 1 for any angle in sine or into cosine. Our third property is this graph is symmetric. This graph is symmetric with respect to, what do you guys think? The x-axis, the y-axis, or the origin? Which one? The y-axis, good. It's symmetric with respect to the y-axis. So you can picture here that this y-axis is acting as a mirror, and this side of the graph is a mirror image of this side of the graph. We know from last lecture that cosine is an even function. And it is true that every even function has y-axis symmetry. The easy way of remembering this is by thinking about a really easy function that you know from Math 126. So if we think about y is equal to x squared, or f of x is equal to x squared, we know that's just this simple parabola. This parabola has symmetry with respect to the y-axis. This is an even function. So it is true that every even function is symmetric with respect to the y-axis. And if a function is symmetric with respect to the y-axis, then it is even. Okay, so if you have a hard time keeping all these separate in your mind, think about a simple example, and then you can apply that to other problems. The fourth property, we already know this, the period is 2 pi. And then the fifth property here is the intercepts. The x-intercepts here. I don't need a comma. Your book lists them out like this: -3 pi over 2, -pi over 2, pi over 2, 3 pi over 2, ... I'll never ask you to list these out on an exam, but I would say it more succinctly as every odd multiple of pi over 2. So the x-intercepts are odd multiples of pi over 2. The y-intercept we can see from the graph is 1. So remember from Math 126, a function can have more than one x-intercept, but a function will never have more than one y-intercept. Otherwise, it's no longer a function. It doesn't pass the vertical line test, okay? So all of these, cosine and sine and tangent, they all have infinite x-intercepts, and they might only have at most one y-intercept. All right, any questions on our graph of cosine? Okay, so what we did so far is we graphed plain old y is equal to sine of x and plain old y is equal to cosine of x. Now what we want to do is graph more complicated things. So our goal is to graph things like maybe y is equal to 5 sine of pi over 3x plus 2. That's our goal, okay? So what we're going to do is start with the base functions, just plain old sine of x, just plain old cosine of x. And then we're going to ask ourselves, what do these numbers do to that base function? Now, you'll remember in Math 126, we covered a section on graphing using transformations. So graphing using transformations in 126 was shifts up, down, left, right, stretches and compressions. Okay, so what I'm going to do is put up the page with all of the transformations from Math 126. We'll review these briefly, but you should all have these memorized from your last math class. Remember, my notes are posted on my math lab. So if you don't have this memorized and you want to get this from my notes later, you can print this out online, but you guys should all already know these. So in Math 126, section 2.5, we did graphing using transformations. So I'm going to call just the plain old function the base function. So just the base function would just be sine and cosine. Yep, and somebody already nailed it in the chat here, up to stretched by 5. Yep. Okay, so remember, if we have our base function and we multiply by some number outside the function, what we're doing is we're literally taking these y values and we're making them bigger if we multiply by something greater than 1. So if we multiply by 2 or 3, we're making those y values bigger. That's a vertical stretch. If we multiply by something between 0 and 1, say 1/2, we're taking those y values, we're making them smaller. That's called a vertical compression. If we multiply x inside the function by some value, this is a horizontal stretch or compression. So the way you can picture this is when we multiply x by some number, we're changing the rate at which our x values occur. So if we multiply by something between 0 and 1, then our x values are going to occur slower and we're stretching it out. If we multiply by something greater than 1, the x values are going to occur quicker, and that's a horizontal compression. Usually the way that I remember these, which is which, this vertical stretch and this vertical compression, this makes sense, right? If we multiply by 2, those y values are getting bigger. If we multiply by 1/2, those y values are getting smaller. Usually I just think the horizontal stretch and compression are flipped. The next type of transformation we have is reflections across the x and y axis. So again, think about what this is doing. If we multiply our y values by a negative sign, all of our positive y values up here are now down here. That's a reflection over the x-axis. If we multiply x by a negative sign, we have all these positive x's over here. They're now negative. That's a reflection over the y-axis. If we add or subtract a number outside the function, that's a shift up or down, right? We're just adding something to the y values. These are the transformations we'll cover today. And then shifts left and shift right, these are called phase shifts when they apply to trigonometric functions. Those are covered in a separate section, section 6.6. Okay, so those are all of our transformations from Math 126. Again, you should have them all memorized at this point. You're going to use these a lot in your math career. Any questions? Okay, so when we have functions of the form sine and cosine multiplied by some number outside the function, inside the function, we refer to these as sinusoidal functions. So graphing sinusoidal functions. And for those of you moving on to physics and engineering, this is going to be really important. A lot of things in physics classes actually is modeled by sinusoidal functions. So things like wave motions, things like pendulum motion. So you are going to see this again. And your classmate here said my example would be stretched by 5 and horizontally compressed by pi over 3. And that's exactly right. So we'll do problems of that type in just a minute here. Okay, so our goal is to graph y is equal to a sine of omega x and y is equal to a cosine of omega x. This is a lowercase Greek letter omega. It actually maybe looks something more like that, like a little W. On your homework, you might see it in bold print. Sometimes they do the Greek letters in some bold print. But usually when you're in physics and engineering classes, you'll see these same variables. So A is going to be this letter out in front, and then usually we have an omega next to the x. Okay, so first up, A, when we multiply the outside of a function by some number, that corresponds to a vertical stretch or a vertical compression. Usually we just say stretch, and then if it's a number between 0 and 1, it's a compression, but it's a stretch downward. So we'll say vertical stretch usually. The absolute value of A is called the amplitude. So A for amplitude. Amplitude tells us how high the wave of the graph is, okay? So absolute value means we just take the number without the sign. The sign, if we had a negative, would correspond to a reflection. So we just take that number without the sign and we refer to that as the amplitude. That's the height of the wave. And I'll show you this on our graphs. All right, the next important thing is going to be the period for us. The period is given by the variable t. Now, maybe you're wondering, t, why not p? Okay, so what I want you to think about is when you see the period is t, think about t as time to complete one cycle. Okay, so t, time to complete one cycle. What we're gonna do is we're going to take our original period for sine and cosine. So sine and cosine, what's our original period for just plain old sine and plain old cosine? Shout it out. 2 pi. Okay, so what we're going to do is take our original period 2 pi, and now this omega in here, as your classmate typed in, this corresponds to a horizontal stretch or compression. Okay, so we need to take our period and we need to change that by a factor of omega. And we'll do plenty of examples and this will make sense by the end of this lecture for sure. So let's take a quick look at an example here. If we have y is equal to 3 cosine of pi x, our amplitude is given by a, which is the number in front here. So the amplitude here would be 3. This tells us the height of our curve, or sometimes you hear this referred to as a sine or cosine wave. To find our period, we would need to set up that our period t is our original period, which is 2 pi. We need to change that by a factor of omega. In this example, omega is pi. So we'd get that our period is 2. This is the time to complete one cycle. Okay, so we're going to use these shortcuts. We're going to figure out what the amplitude is, figure out what the period is, and then we know what the basic shape of sine and cosine are. We're going to use all these shortcuts to graph really quickly. We don't actually have to start with sine and then figure out what the compression and the stretch looks like. We'll do it much quicker using all of the shortcuts. And again, on your homework, I really encourage you to draw these by hand and then go to the graphing tool. For those of you that are taking more math and physics and engineering, you need to know how to do this. Anybody need more time on this page? Okay, so let's just jump right in and we'll use all of these shortcuts to do some graphs quite easily. So let's graph y is equal to 9 times sine of pi over 3x. All right, our first step, we're going to use the amplitude A to determine where the max and the mins of the graph are. In other words, the height of the wave. All right, so help me out with this one, guys. Our amplitude here is equal to what? Shout it out. 9. Okay, this is what we're going to use to label our y-axis. So previously, sine and cosine, the max and the mins were 1 and -1. Now they're going to be 9 and -9. Our next step, step 2, is to find the period. To find the period, we need to set up t. T is equal to our original period of plain old sine or cosine is 2 pi. And we need to change that by our horizontal stretch or compression, which is going to be a factor of omega. Omega in this example is pi over 3. Now I'll tell you the number one mistake I see students make. They can set this up, and one of the most common mistakes I see in this entire chapter 6 is that students get stuck on the division here. So take the time to do the division. If you need to write this out by hand, please do so. So I'll do this the long way. In order to divide with fractions, what we want to do is write the numerator first, switch to multiplication, and then we want to flip the denominator. So instead of pi over 3, I'm going to multiply by the reciprocal, which is 3 over pi. So please take this extra step if you need it. Now, we notice that the pi's cancel out, and as I mentioned, I think on the first day of class, we will never see something this semester that has a pi squared in it. So if you ever forget to flip and you end up with a pi squared, that's just a really good self-check, okay? So things should work out somewhat nicely. 2 times 3 is 6. So our period here is 6. That's going to be the time to complete one cycle. Now, in order to graph this, what I want to do is figure out where my key points are. Key points. Our key points come from our quadrantal angles. Our key points come from our quadrantal angles. Quad means how many? 4. Okay, so my step 3, this is the key step here. I need to split my period into 4 intervals. It will always, always, always be split into 4 intervals, always, because that's our key points come from those quadrantal angles. Okay, so what I'm always going to do is take my period t and divide by 4. So my period here is 6. Divide that by 4. That gives me 3/2. This is how I'm going to label my x-axis. So when I split that period into 4 intervals, that tells me where those key points occur. So those key points occur, that's what I want to put on my x-axis. All right, any questions so far? Okay, our next step 4, we'll plot our key points. Step 5, connect and repeat. Step 6 is if you have any other transformations. So if we have any shifts up or down or reflections, we'll do those last. Okay. Okay, so the first thing I'm going to do is we figured out in step 1 that our max and mins were at 9 and -9. So on my y-axis here, I'm just going to put a 9 and I'm going to put a -9. The next thing we want to do is label our x-axis. I'm going to label by 3/2. So what I'm going to do is 3/2 times 1, 3/2 times 2, 3/2 times 3, etc. Okay, and I'm going to reduce as I go. So 3/2 times 1 is 3/2. 3/2 times 2 is 3. 3/2 times 3 is 9/2. 3/2 times 4 is 12/2, which reduces to 6. What am I up to? 1, 2, 3, 4. 5 gives me 15/2. Times 6 gives me 9. Okay, once we have the x-axis labeled, what we want to do is plot our key points. So we are graphing sine. We are graphing sine. So what we want to do is look at our general shape of sine and just copy that pattern in. So this was our graph from last lecture. Our pattern for sine was 0, max, 0, min, 0. Okay, so 0, max, 0, min, 0. What I'm going to do is just copy that pattern right in. So here we go. 0, max, 0, min, 0. So here's our key points. We figured out in step 2, our period was 6. So we nailed it, right? We have one period done right at 6. So those are our key points. Step 5 is connect this and repeat this. So connect, repeat. And then step 6 is any other transformation. So if we happen to, at the end of this graph, have plus or minus some number or reflection, we would do that last. So there's our graph. You notice here our domain is always going to be all real numbers for sine and cosine. The range, the y values we actually hit, we hit from -9 up to +9. Any questions on this graph? 1, 2, 3. Any questions? Okay, let's do a couple more sinusoidal functions. Anybody need more time on this page? Okay. Next one. Let's graph y is equal to -5 sine of 2x. Okay, so our first step, we'll use A to determine where the max and the mins are. In other words, what the height of the wave is. All right, so A, what we're going to do for the amplitude, we're going to take the absolute value of that number in front. So remember, the absolute value is just going to be the number without the sign. So in this case, we're multiplying by -5. We're just going to take the absolute value of -5. And so we're going to say that our absolute value is 5. So you should always have a positive amplitude. This negative corresponds to a reflection later on. We always would just give amplitude just the absolute value of that number. This tells us how to label our y-axis. Step 2, we'll find our period. Okay, so what we want to do to find our period, we're always going to start with the period of just the plain old trig function. So here we have sine. So what's our normal period of just plain old sine? What's a normal period of plain old sine? 2 pi, good. And what we want to do is take that period and we need to consider this horizontal stretch or compression. So we're going to change that by a factor of omega. In this example, omega was 2. So that means our period is pi. This is our time to complete one cycle. So as we look at the graph, when x hits pi, every pi, we should complete one cycle. The next step is the most important step to get these graphs correct by hand. We're always going to take our period and split it into how many intervals? 4. This is because of our 4 quadrantal angles, our 4 key points. We're going to split this into 4 intervals. Okay, so we always take our period t and divide by the number 4. This never changes, whether we're doing sine, cosine, tangent, cosecant, secant, cotangent, we always want to split this into 4. So we figured out in step 2, our period is pi. We want to divide that by 4. This tells us how to label our x-axis. In other words, where those key points are going to occur. Also for your exam next week, if you want to bring highlighters or colored pencils or whatever writing utensils with you, if that helps you out, feel free to do that. Okay, step 4, we'll plot our key points. Step 5, we'll connect and repeat. And step 6, we'll do any other transformations we have. How about this one? Do we have another transformation that I missed? Yes. What do we have right here? A negative out front corresponds to what on our graph? A reflection. Okay, we have 2 types of reflection, either reflection over the x-axis or the y-axis. So what you want to think about is we have all of these output values, all of these y values. So here I'm pretending I have a graph. Here's my y values. Now instead of being positive, I'm making them negative. So all these y values up here are going to move down here. If we had a negative y value, we multiply by a negative, it's now moving up here. So this is a reflection over which axis? The x-axis. So in this one, we need to remember we have a reflection over the x-axis. We'll do that last. Great. Any questions so far? All right, let's put this bad boy up. Okay, so first up in step 1, we figured out that our amplitude was 5. So I'm going to put 5 and -5 up on my y-axis. Of course, if you're doing this by hand, you could put 1, 2, 3, 4, 5, -1, -2, -3, -4, -5. But if it was me, these are the key points. That's plenty. We figured out we should label our x-axis by pi's over 4. So I'm going to count by 1 pi over 4, 2 pi over 4, 3 pi over 4, reducing as I go. It is typical to label this with radians and not degrees. So pi over 4, 2 pi over 4 is pi over 2, 3 pi over 4, 4 pi over 4 is pi, 5 pi over 4, 6 pi over 4 is 3 pi over 2, 7 pi over 4, and then 8 pi over 4 is 2 pi. That's plenty. If you did have this on paper, typically I ask my students to show me 2 full cycles, 2 periods. So this is plenty. On my math lab, you have a graphing tool. Okay, our next step is to plot our key points. So we are graphing sine. So what we want to do is look at our pattern for plain old sine, and we'll do one with cosine next so we can see the difference. So to plot our key points, step 4, this is our graph of plain old sine. Our pattern for sine is 0, max, 0, min, 0. What I'm going to do is copy that pattern over. So here we go. I got 0, max, 0, min, 0. We should check that in step 2, we found our period was pi. We finished 1 cycle of this right at pi, nailed it. If we continue this, we should finish our second period by 2 pi, looks perfect. Remember, if you turn this graph sideways, you'll have an S around the origin. So we can check that as well. We have one more transformation. We have our flexion over the x-axis. So I'm going to do this in a different colored pen. This black line is not my final answer. If I take this black graph and I reflect it over the x-axis, my final answer will actually look like this. If you were doing this on a paper quiz or a paper test, My suggestion would be to you is once you get your final answer, I would erase out the first line and only leave your final answer there so that it's very clear which one your final answer is. And if I was smart, I would have brought a pencil today, and I did. I just forgot about it until right now. So I'll do that on the next examples for you guys. Any questions on how I got this graph? Okay, let's do one more. Okay, next one, let's graph y is equal to 3 cosine of 6x plus 2. Step 1, we'll find out what our amplitude is. So help me out with this. The amplitude of this is what? Go ahead and shout it out. 3. I'm going to use this to label what? My x or my y-axis? The y-axis. Great. Our second step is to find our period. Our period, we're always going to take our regular period for plain old sine and cosine, which is just 2 pi. And I need to divide by a factor of omega. In this example, omega is 6. That gives you my period is pi over 3. That's the time to complete one cycle on our graph. The next step is I always take my period and divide into how many intervals. What should I divide by here? What number? 4, good. Okay, so it's always, always, always our period divided by 4, always, because that's where our key points, those quadrantal angles, come from. Okay, so our period is pi over 3. We want to divide by 4. Again, one of the most common students' mistakes I see in this entire chapter is doing this division. So please take this extra step if you need to. We start by writing our numerator, switching to multiplication, and then we multiply by the reciprocal of the denominator. So the reciprocal of 4 is 1/4. That gives me pi over 12. This tells me how to label what? The x-axis. Good. Okay, step 4 is to plot our key points. Step 5 is to connect and repeat. Step 6 is any other transformations. What transformation have I missed? What other transformation do we have in this example? The +2 is a shift. In which direction? Up, down, left, or right? Up. Good. So what you want to think about is you just have a bunch of y values you're adding 2 to, so they just move up 2. So we need to remember under the other, we have a shift up. So we'll do that last. Okay, so first thing we'll do is label our axes. So this one's a little bit different than the last two. We know that our amplitude, the height of the wave, is 3, but we also want to keep in mind that we have to do a shift up. So if we only put 3 and -3, that's going to be hard to get the shift up. So I'll actually on this one label 1, 2, 3, 4, 5, -1, -2, -3. And as a reminder to myself, if I want, I can highlight that we're starting with 3 and -3. If that's helpful to you, feel free to do that. Okay, next thing, I'm going to label my x-axis by pi's over 12. So 1 pi over 12, 2 pi over 12, 3 pi over 12, etc., reducing as I go. So 1 pi over 12, 2 pi over 12 is pi over 6. 3 pi over 12 is pi over 4. 4 pi over 12 is pi over 3. 5 pi over 12, and then 6 pi over 12 is pi over 2. Okay, next thing we'll do is we'll put in our key points. We'll connect and repeat, and then we'll do our other transformations. So we are graphing cosine. We are graphing cosine. So what we want to do is go back to our graph of just plain old cosine and look at what the pattern is. So here's our graph of plain old cosine. Our pattern is max, 0, min, 0, max. Okay, so max, 0, min, 0, max, which is different than our pattern for sine. So we're going to copy and paste that in. So for cosine, we have max, 0, min, 0, max. And we'll continue this pattern in both directions. Now we can check around the origin. That looks like a C if we turn it sideways, so that's right. Our last transformation is our shift up. So I'm going to take all of these values and I'm going to shift them up too. So the easiest ones to do are kind of these peaks and these troughs. So these points at 3, I'm going to move them up to 5. These points that are at 0, I'm going to move them up to 2. And these points that were at -3, I'll move those up to -1. So my final answer looks like that. If you were doing this for a quiz or a test, you should erase out or somehow indicate which one of those graphs is your final answer. So maybe I do something like that. Now the amplitude we said was 3. If we look at this new graph, if we look at the distance from the center up to the top, that's still 3, or the distance from the center down to the bottom, that's still 3. So we still refer to the amplitude as 3, the height of the wave is 3, even though we've shifted it up.